Okay, so we're going to look at Lisp, and I've already given you a tour of Lisp, and you've started on your implementation, so you understand Lisp to some degree there. And if we were to just look at programming in Lisp, that introduction I gave was probably enough for you to go to the Common Lisp manual and go and understand how Lisp works. Okay. So what's going to be different in what I'm going to talk about is that I'm going to actually talk about implementation. Okay, so we're going to continue with our exploration of the Lisp interpreter, but we're going to move to a very different direction. So far, we've been looking at scoping issues, evaluation issues, things having to do with serial languages, and we're going to now look at concurrency. Okay, that's one of the things we touched on when we started the course, and we motivated concurrency in this course by, again, through programming language concepts. We said, look, when we have some expression that needs to be evaluated, which is a compound expression, or we have a list of expressions to evaluate in general. The languages dictate that the expressions be evaluated from left to right. Okay, and the order is important because there might be side effects. Okay, but if there are no side effects, we can have variations on this order. We can have lazy evaluation, where we evaluate something only on demand. Okay, that's something we might, and I'm hoping we will touch on later. And we can have eager evaluation, where we actually evaluate them in parallel. Okay, and so get some concurrency. And we saw that lazy evaluation is actually supported for the OR operator here. The second operand is evaluated only if necessary in most languages. And eager was something we haven't seen in languages so far, and there's no good definition of eager that I could find. So we'll just define it ourselves. Okay. And so to motivate eager evaluation, we looked at concurrency constructs. And there are special parallel languages, okay, that we can use, but they mainly provide syntax, and the basic semantics are provided through libraries in Java. Okay, so let's just understand those libraries, and we can try to understand later how we can implement higher level constructs. Okay, so some of you have dealt with concurrency before, many of you hadn't. But we saw concurrency earlier on in the course, so by now you know it at a theoretical level at least. The goal of assignment 4 is to actually teach you how to use concurrency, and so that the concurrency part will be a required part. So whatever I've got in A4 so far is optional. It's just allowing you to put the icing on the cake of stuff you already know, and distribution and concurrency will be the required parts. Okay, we haven't covered how to use these two concepts exactly in class. We've covered them in the overview section. Need to give you a few more details. So concurrency is the big deal in assignment 4 actually. Distribution is an easy part. So how do we get concurrency? Well, we can tie it to lambda expressions. And the idea is to create a new stack, and we need to provide the base of the stack. Okay, so when we write regular Java programs, there is a stack that's already created for us, and its base is the main method. Okay, with concurrent primitives, you can create new stacks, and to create a new stack, in Java you just say new thread, and then you start it. Okay? And the thread needs to know what to do. What to do is decided by you. So you give it a lambda expression here, and that lambda expression is executed as the base of the stack. Okay? So our lambda expression here is basically like the lambdas we saw in Lisp. Now that we know Lisp, what goes before the arrow are the arguments to the lambda. And what goes after the arrow is the body of the lambda. Okay, in this case, we there are no arguments, so the two parentheses have nothing in between. So that's the lambda expression we gave, and we said when what we want to do is execute. We can put a piece of code right there, but we've written this class modularly, so we've actually got a run method, which is not a public method here, and that run method is called by the body of the lambda. Okay. So that's just refreshing what we saw earlier. Okay, any questions? Okay. So creating a thread isn't hard, as we see here. Okay. The tricky part is synchronization, because when you have multiple threads, they can interfere with each other. So we might want one to wait whilst some other thread is executing. Okay. And there's two kinds of synchronization. One is to ensure mutual exclusion. So you're trying to make sure two threads don't tread on each other's toes. They don't know about each other necessarily. They're not trying to work together to do some larger task. We just want to make sure that they don't get in each other's ways. Okay. So if that happens, you can go and declare a method that acts, and it happens in programming languages in programs by accessing shared data structures. So if there is a method that can be executed if there's a set of methods that can be executed in a class that can be executed that share some data structure, then we make all of these methods synchronized, okay? Which ensures that only one of them will execute at any one time. So only one of them will gain access to the shared data structure. So that allows us to make sure that we safely access data structures. We may also want thread cooperation, where one thread is waiting for some other thread to do something before it proceeds. And for that, we have wait and notify. Every object has a wait and notify method, and wait will go in and block the executing thread in a queue associated with the object, and notify will go and unblock the first blocked thread associated with their object. If there is no blocked thread, notify is a no. Okay. So wait and notify access a common queue associated with the object. That queue is a shared data structure whose consistency must be ensured. So wait and notify must be executed in synchronized pieces of code. Okay, that's a requirement. Yes, questions? So the example details you've forgotten. At this point, the important point are the constructs. Okay, and in Java we can use a synchronized keyword to get exclusive access of a piece of code. Some of you might have seen another construct in Java that allows us to have mutual exclusion. So wait, notify, and synchronized keyword in a method header. That's something we've seen. We saw earlier, and we're seeing again right now. Anything else that you guys might have seen who've done concurrency? Mutual access we want to have exclusive access, not of the whole procedure, but a piece of the procedure. Yeah. Sorry? So mutex is something that you can build using the synchronized wait and notify thing. So that's something you studied in operating systems or some other place. It doesn't exist directly in Java, but you can implement it in Java. But in Java, there is something else that's a language level which allows you to get, and mutex is a way to get access, exclusive access, yeah. So sockets need threads to make them work properly, and then they need these primitives. They don't by themselves provide these primitives. So if you haven't seen it, that's fine. You can also do something like this. So you can go and take any piece of code and synchronize it. Okay, so a procedure can be synchronized. That's the whole procedure. You can take any piece of code within curly braces and put the synchronized keyword followed by which object you want to synchronize on. So I can be invoking this method in one object, and I try to get the synchronized lock of another object. Okay, typically you do synchronize this. That's what I'm doing here. So synchronize this is equivalent to what I saw earlier, but synchronize this can surround any piece of code in a method. It doesn't have to enclose the whole code as I've seen here. Okay, and like I told you, people don't like to declare things. So people create inner classes and so forth. So if you don't want to create a procedure out of some piece of code that needs some exclusive access, you just put the synchronize this keyword around it. Okay, so that's what this is. And we'll be using this in my examples just because that saves me space. Okay, so these concepts are not hard to understand. I teach this in 401. People teach concurrency in 110 like courses also. And some of you have seen these concepts in operating systems. And how just as you learn most of the Java language primitives in 110, but how to use them, you learn in more advanced courses because there are advanced ways of using them. So, so the tricky part here is understanding how to use synchronize, wait, and notify. How they work is not so hard to understand. Okay, at least at the level I've described. There are some subtleties that I'm not getting into. So, what we'll see through the following slides is we'll take this problem of eager evaluation, and through that understand some of the subtleties of concurrency. Okay. Any questions about the semantics of the primitives? Okay, so these allow you to synchronize any block. An argument to synchronize determines the locked object in queue. Okay, so I use lambdas to create the thread, and lambdas are something that got added to Java relatively recently. I think it was 1.8, and threads have existed much before that. Okay, so there must have been a way to do threads without lambdas. And when we looked at concurrency last, that other alternative was mentioned, which is to create a runnable object. Okay, so what we can do instead of using lambda expressions, and we saw this last time, so I'm not going into depth here again. So rather than saying new thread and give a lambda expression, I'm saying new thread, and I'm giving an instance of something that is an object that is an instance of a runnable interface. Okay, what's a runnable interface? That's a predefined Java interface that has one method called run, which takes no arguments. Okay, so if I'm going to pass this to thread, I must, in this class, implement runnable, okay, which I have done. And it was very easy for me to go from the previous code to this code because I had a method called run already. It was protected there. It was called by the lambda expression. I just make it public, and it all works. Okay, so that's an alternative way of doing threads, and that's a more flexible way. We're going to use that in our eager evaluation, but I do want to mention this. And so, questions about this? Okay. Again, we are providing the base of the stack. It can be a lambda expression, or which is an anonymous piece of code, or it can be a named method, which is what we're doing. So one question that arises is that, does thread provide two constructors, one that takes runnable as an argument and one that takes lambda as an argument? And the answer is no. It provides only one constructor, thread that takes runnable as an argument. So what do you think happened when I passed a lambda to the thread constructor? And we'll go into depth later of how lambda is implemented in Java. Okay. Yeah. It created a class with a name given by it with that method. And that method essentially, the body of that method has the lambda in it. Okay, and the idea of creating methods under the cover, I mean, is that something you've seen in, or let me put it this way, you have seen that before also. Anybody who's dealt with Java has seen this concept before, that you write one piece of code and what is generated, and you write a set of methods and what is generated is a superset of those methods. So the source code and the compiled code don't correspond one-to-one in terms of the number of methods. This is 110 stuff. If you ever used 110, you have used it, you just don't remember it. Do you have to have a constructor declared in each class? Default constructor is generated automatically in the object code for you. Okay? This is in the same spirit, so there's nothing different here. That if you don't provide a constructor, Java will provide a constructor. Okay? So we'll look into exactly how it's done. I actually managed to figure that out, okay, by looking at the object code and converting it back into source. So lambda expression automatically converted to public method in the expected interface. Okay, so OR is something we can do eager evaluation on. What other operations can you do eager evaluation on possibly? And sorry, a little louder. Not takes only one argument. Okay, so any operation with multiple operands. Okay, so and plus list, funcall, direct call of defunct functions, curry, they all can be used for, can do eager evaluation. Okay, so in all of these cases, we have a list of arguments that we want to process in concurrently. Okay, so any multi-operand basic operation, as long as we don't have any side effects, and if we have side effects, we can try to sort of define how to handle them. Okay, so in all cases, we must evaluate a list of expressions. So let's try to understand how this is done. Okay, might be missing some curly braces here. So what I'm saying here is that, look, we've got a list of expressions, E0 to En. Okay, I'm counting from 0 and ending at n, which together I'm referring to as E-eval, which is what I want to get out. And evaluate serial is the method I'm calling. And what I want to evaluate is E, which is a list that has E0 to En. Okay, so I want to get the evaluation of all of these. Okay, that's my goal in some environment. So what do I do serially? I go from 0 to n. Okay, and I just go and evaluate each of these elements one by one. Okay, that's my serial evaluate. Okay, and now I want to go and do a parallel evaluation. So we have to figure out how to do that. Okay, these slides, I have no idea how they're going to turn out. They barely got ready before class. Andrew and I were discussing the design of this whole thing till late last night. So we'll see what happens here. So this thing in purple was supposed to come later, but I want to do this in parallel. Okay. So given what you know, what should evaluate parallel, and I can do that with lambda, or I can do that with explicit runnable. Okay, so let's do it lambda first, then we'll go and do the explicit runnable, and this will help us determine when to use lambdas, when to use explicit runnables, perhaps. Okay. So I'm given E0 to En. We know what we have to do with serial evaluation. So what should I do now here? What are some of the things I need to do here? So I'm doing this in Java, and we can do this inefficiently or efficiently. Just think of a way of doing it. So I have n plus 1 expressions to evaluate. Andrew?
We have like a while loop that loops through, and then we do parallel eval on each of the different heads.
So basically we want to go in, we want to evaluate each of these expressions in parallel. And what Java construct will I use to do that? Yeah.
You need to spawn more threads.
So I'll spawn threads, right? I will do new thread. How many threads will I need given that I have n plus 1 things to evaluate? How many threads should I spawn? And we'll do it a little smarter than what most languages do.
Doesn't it depend on how many? You can do however many you want. You can do like 2 or 3 or n plus 1.
So I can do 2, 3, or n plus 1. Should I do more than n plus 1?
No.
Should I do n plus 1? If I can?
No, because I guess on the main thread you could do the first one.
So a lot of languages create n plus 1 threads, where we'll do create n threads. Okay? And so I created these threads, and each thread must execute something, right? So each thread must know what to evaluate. So somehow I have to go and give a lambda expression to that thread, saying this is the value you actually evaluate. So what should that lambda expression be like? So there are two questions here. What should that lambda expression be like that I pass to each thread? And after I've created the threads, what do I need? Do I need any synchronization at all? So do I need any synchronization? Do I first need the threads to be synchronized with each other somehow, that they don't tread on each other's toes? So each thread is evaluating so thread I is evaluating EI, right? If these expressions are independent, there's really no synchronization needed right there. Now threads are going to work in parallel. I have to go and return an array. This method is supposed to return an array of all the evaluated threads. So do I need any synchronization? Here's the parent thread. It's going to spawn children threads. Each child thread is going to evaluate one of the expressions. The parent thread is supposed to return you the list of all evaluated expressions.
Yeah, I mean the parent thread needs to wait for the children threads, so.
It has to wait for all the children threads, right? So, and we have the wait method on a thread. We can do wait on an object, but now we need kind of a wait all. Okay, that we want to wait on all the threads. So what is synchronization? So it has to wait. If it has to wait, do the threads have to do something to make it unblock then? How does it wait? If it waits, how does it unblock? So it waits. It has to call some kind of wait on some object. How do we make sure that what ensures that wait unblocks? I mean, we have to design something. So there's one person whose brain is clicking away. Yeah.
Yeah, I'm sure that the thread would need to terminate correctly and then properly send a message to the parent thread saying.
So the thread when it finishes, it has to send a message. What primitives do we have? We have new thread, and what other primitives do we have? We have the synchronized keyword, and we have wait and notify. So the parent thread has to do wait on some object. We don't know what that object is right now. Okay, but we know it has to do a wait there. And the children threads, each child thread must do what then? Sorry? A notify. But and on the same object, and the weight. So how do we make sure that the weight waits for all of the notifiers? Yeah.
I think you need a counter.
So you need a counter. So this object that we are talking about has to count how many notifiers to get. Okay. So we've got that. Okay. This was the trickiest part of the whole lecture. Okay. So we do the following. We go and create. We create a new thread. Okay. And we say, look, why don't you go and evaluate each thread is bound to a particular I. Okay. And it gets the whole, and it basically goes and evaluates the expression at that I. Okay. So that's what it's doing with a lambda expression. Okay. So that's but we need now to also wait. So and like it was mentioned, like Mac mentioned, that the parent thread will go and evaluate the 0th element. Okay, so we create only n threads. But after it's evaluated, it can't just return. So there's this magic object that is going to do a wait on. And do you want to give that object a name? This is an object that has the count. So it's going to call some method in that object that is going to do a wait. So what will be a good name for the object and a good name for the method to be called in that object? That method will call wait, but is there a better name to sort of explain what's really happening? That the parent thread is waiting for all the children to finish. So you guys might have, yeah.
Talking about join.
So where did you study that, in operating systems?
Yeah.
No. Okay. Okay, so we'll go and have a join object. Okay. And we'll give to the join object the count, that there's going to be n minus 1 threads that I want to join with. We'll do a joiner.join. And then what I've got one blank piece left. What should go in this blank box that I have left? Sorry? So joiner.finished. Finish will go and call notify. Okay? So there's this magic joiner object that you guys have to implement. Okay? But we know the semantics right here. Okay? Questions? Yeah.
Why is it n minus 1 joiner instead of n? Because you are waiting from 1 to n. There are 10 threads you need to wait.
You know, I used n in two different ways, so you're right. I have n plus 1 threads. So it'll be joiner n and not n minus 1. Good. Okay? Yeah.
Essentially, the finished function is just add a counter join.
Sorry?
So what's inside the finished function?
So the joiner object, so the joiner object is a black box for us right now. Okay? And that's something you have to implement. Okay? But you can imagine that the finished method is going to call notifies. And the join method is going to call wait. Okay? And any more questions on this? I've got some, I'm going to give you some details of the joiner object, but not all, so that there's something for you to also work on. Okay? But as you mentioned, this should be n and not n minus 1. Okay. So actually, let's go and try to understand, again, my animations are a bit off. Assuming this all works, I think I've got a slide later describing what joiner should do, okay, which we kind of have figured out. Let's try to figure out what happens to this piece of code, which has side effects. Okay, if there's no side effects, parallel evaluation and serial evaluation should yield the same results. Okay, if there are side effects, they should yield different things. Okay, so given this piece of code in serial evaluation, what should I get back? I'm saying set q a0, then I'm constructing a list of two set q calls, and each set q call increments a and assigns the incremented value to a. Okay, so I have two increments, and the result of the first set q is the first element of the list returned, and the result of the second set q is the second element of the list returned. So in serial evaluation, the result would be and now what will happen in parallel evaluation? What can happen? There's more than one choice. You can get 1, 1, and what else can you get? Can you get 1, 2? So what does parallel evaluation really mean? Parallel evaluation means two threads executing. They could be sharing one processor. Right? So it's not necessarily that they have two processors going at the same pace. They could be one processor, or one processor could go in. There could be two processors, and that evaluate these threads at different times because they have other threads to also serve. So Andrew got the harder one. The easier one is that you can get 1, 2, 2, 1, or 1, 1. Yeah. So why are we going through all this parallel stuff if there's all these problems? So eager evaluation goes with functional programming. Functional programming says no side effects. That's why I postponed set q till so late, simply because that doesn't go very well with things. So people who do functional programming and people who do high performance computing often go together. Okay, and there's something called data flow computers that were invented at MIT a long time ago, and they were based completely. There was a new architecture that was based on functional programming. Okay, so this is just to show you what bad things can happen and why eager evaluation is something you don't want to try and see in Java, but it's something we want to do in the Lisp as long as we make sure we use Lisp as it should be used rather than as how it can be used. Okay, but let's just make sure let's just see how that may happen. So underneath there's multiple instructions to execute. So somewhere A got plus A1 got evaluated, got assigned to some temporary variable, and then we did set q at1. That's what essentially happened underneath, right? And this can occur serially. If it occurs serially, then we will get 1, 2. If the first thread goes in, increments A first, and the second thread executes A next. Okay. If the second thread gets scheduled first, and the first thread gets scheduled later, that can happen. We'll get 2, 1. And this is the case that this is the most subtle case that Andrew pointed to. That basically each of them incremented A without having assigned to A. Okay, before they're assigned to A, and then yeah.
So then would the value of A after the evaluation still be 1 or be 2
At this point, what do you think?
I would think it would still be 1.
Yeah, so that's why it's 1, 1. So that was your first guess. That's typically people's last guess. People typically get 1, 2, and 2, 1. So you guys now understand why you need synchronization, and also the damage. So anyway, this is what happens here. And you guys understand this part? Okay, this is actually quite subtle. That, I mean, this is how synchronization works. If you haven't seen before, Typically, students are surprised by this. So how to ensure deterministic evaluation with side effects? How could we ensure that? And we could do that. We could do this. I said this motive-based synchronization. I could just go and say synchronize this and evaluate this lambda block in a synchronized block. Yeah. And do you like that? Why not? Sorry? So I did all this overhead of creating these thread objects, these join objects, and what do I end up doing? Serial evaluation. Right? So this defeats the purpose. Okay. Do you have a question? Okay. So synchronize, evaluate, serializes execution. Okay, so we don't want this. By the way, I have to go and change all this n-1 to n everywhere, so just remember this, and if I forget, that's an error. What else can I do? If I want to go and ensure that this is deterministic. What if I always want to ensure it's 1, 1? No matter in what order they execute, what could I do? Something that you guys have seen in the last lecture, we could use, yeah.
You come and save the state of each time for execution.
So you could go and, how do you save state? The state is kept in what kind of object? No, the state is the value of the variable A, right? It is, or environment. And do we know how to save environment? We studied last time the idea of deep copy, okay, a copy. And again, we could do copy on demand. Okay, I'm actually thinking of how to give you guys an extra credit feature based on copy on demand. I think I figured it out. So we could do an environment equals environment.copy, and then we will. It's more expensive, okay, but we can have copy on demand as Robert suggested last time. So anyway, this is a problem with parallel evaluation, and this is one way to solve it. Okay, again, I didn't find anything anywhere that says this is the way eager evaluation should go. So this is just something from first principles. Okay, so I don't know what languages really do. I don't know if any language really does eager evaluation. Like I told you, I know about data flow computers. And some of you might have studied asynchronous computers that Montec does, which is on the same spirit. But I don't know of any practical language that does this, so I can't tell you this is how a language does. So I'm just giving you the choices. Okay. And in the assignment, I'll give you choice of copying or not copying your environment. Okay. Questions so far? Okay. So what does this joiner do? And I'm not giving you the exact code here, but there's a constructor that initializes a count, okay? And the finished and joins are related to each other. And what is the relationship between joins and finished and given a count? So what's the relationship between finished and joins given a count? So if n is the count, joiner waits for how many finishes? Okay. So join blocks joiner, which is let's call it the parent thread. Count number of until count number of finished calls have been made by the children or by basically the finishers. Okay. So join is called by some thread which blocks. Finish is called by multiple threads, and until n finishes have been called, join blocks. Okay, and you have to consider the case where the join was called before before the finish was called. Okay, and before any finish is called, and also the case where join is called after all finishes have been called. Okay, so in your thing you have to keep a variable that, and the variable is already kept for you actually, but you have to go and check the variable because you do want to consider the cases. We don't know in what order they'll be scheduled. So finishes may all be called before join even gets a chance to be called. Okay, so you have to consider that situation. So I won't give you the pseudocode for this, but this I've given you enough hint, I think, to figure it out. Okay. Questions? Okay. So in Java, join and finish use wait and notify and synchronize methods, of course. Okay, just make sure that if you don't put them in synchronized methods, Java will complain and say they should be in synchronized methods. Okay. Questions? Okay. Let's try to understand what we gained by lambda expressions, or what we lost, by saying, how would I go and convert this into code that uses a explicit runnable class? So here I'm saying new thread, and I give to new thread a lambda expression. With an explicit runnable class, I'll have to give it instead a instance of a runnable interface. Okay. So we have to figure out what that runnable class looks like, what its methods will do, and how to interface with it. So we look in some depth later, but can you guys see some issues with creating that class that are easily solved by lambda expressions? Scoping issues. Here, all these variables, I, joiner, they're all in here, directly accessible, right? Now what will have to be done is that somehow these variables have to be accessed by this external class. Is that even possible? So you have an object which has got a run method. So let's go and see that. I mean, this is not this is again 110 programming, guys. So we're going to now do 1 to n. We're still going to have to do something 1 to n. Again, we're going to have a basic joiner with n entries. We're going to start a thread, and the question is, what's the argument to the thread? So I can say new thread, new, and this is my runnable class name. Okay. And then so will this work? The way I've done new? We don't know what's inside S expression evaluator, but there's something wrong already here, the way I've used it. And how does it know? Okay, so the issue that was mentioned earlier, how does it know what to evaluate? What to evaluate is in here, E0, En, and we want this return value here. This class has no idea of what that information is. So the classic way of going and telling some external class and some external method to work on your data is to go and pass that data as arguments to some method. Okay, so I can go and call a method in S expression evaluator and pass it where the result should be stored and what value should be computed. Except we have only one method in this class called run, which takes no arguments. So what's my alternative now? I have to use that class. Run takes no arguments. I just go and somehow tell run to compute on these values. Okay, so this is why I said it was 110 stuff. So how to make different instances, evaluate different expressions and extract a common joiner. Cannot add parameters to thread.run, define done. So I go and create a constructor. And in the constructor, I go and pass these values. And this tells you exactly this tells you something about how lambda expressions are evaluated. Essentially, lambda expressions are evaluated by taking all these local variables that are accessed by the lambda expression and assigning them to instance variables through a constructor in the method generated through the lambda expression. Okay, we'll see that in detail later, but I mentioned this in some depth here just to show you A, the power of lambda expressions, and B, how they're actually processed. Okay? So now with this, there should be, writing that expression evaluator should not be a challenge. Okay, questions? Okay. So that's my expression evaluator. It takes some arguments, assigns them to instance variables, and which instance variables. Here what I've done is all of these things that have the prefix of this are the instance variables, and these were originally local variables. So what were local variables become instance variables in the expression class. Okay. So okay, so we understand runnable, how to do it with runnable and how to do it with lambda expressions. In your assignment, you'll have the choice of doing using either of them. But let's try to understand what's going on here. So supposing my list is one of these operations that does eager evaluation. And I've got this compound list. How many threads will be created here? Four? Anybody disagree? So T1 to do this part, T12 to do this part, T2, T21, and T1 can do the list after T1 and T12 have finished, and T2 can do the second list after T2 and T21 have finished. Right? So 4 threads. Okay. And if I have to, so that is my first expression I entered. If I enter the same expression again, sorry, T1 to go and do the top level list. Okay. So because we are creating n-1 or n-1 threads given n expressions, we are doing a good job with saving number of conserving the number of threads created, and that's a good goal. Are we doing a bad job here in any way? Could we do better than the algorithm I've shown you in terms of thread creation? And not only thread, what about the joiner objects? Objects are expensive. So there are these thread objects I'm creating, there are these joiner objects I'm creating. Threads, after they're created, they terminate. And their objects will be garbage collected, ultimately. Okay, so it's not as if we're doing something really, really bad by creating a lot of threads. But we still want to go and conserve the number of threads we create and the joiner objects we create. So that's why we went and allowed the parent thread to also compute something. But can we do even better? What's something bad we're doing here? For every expression that is to be evaluated, we create a new thread. So the user enters this expression, we created 4 threads. If the user enters, and again we create how many joiners do we create? We create, I didn't ask you guys that question, but we have to have 3 joiners here. Okay. So if I was to re-enter the same expression second again, I create another 4 threads, another 3 joiner objects. So the user went and entered this expression first, and then the user entered the second expression again later, and these 2 expressions are to be evaluated serially. It's not as if these 2 expressions have to be evaluated in parallel. Okay, the user entered an expression, wants to see the result, based on that result wants to enter another expression. Okay, and in this case I've just entered the same expression, which is kind of silly, but that allowed me, I could just copy and paste. But let's say the user enters, you know, the second expression again. We've gone and created another 4 threads, another 3 joiner objects. Okay. And ideally, what could we have done? Somehow reuse those thread objects. Okay. So that's going to be the challenge for the next 20 minutes. Okay. So we want to do the following. So minimum threads and joiner objects need. I'll have to do this all over again, but make sure that I don't. Okay, I won't click another time because I might go to the next slide. So what should we do? How should we, you know, we still have these abstractions, thread abstraction, wait, and notify. What should we do? And this is not easy. If we can figure this out today in 20 minutes, we are doing really well. Okay? And like I told you, Andrew and I were on emailing each other till late last night to get this right. And there are languages that actually allow you to create such abstractions. So what should we do? Tell me all the things we need to do to sort of reuse the threads. Yeah.
Make like a thread or joiner factory.
So have a thread factory or joiner factory. And the idea of having a factory is that when you go to a factory, you can get back an existing thread. Good. That's one concept. Let's go in more depth now. What else do we need to do? Yeah.
Make some kind of thread pool object that has a list of basically threads that are long living.
Okay.
Choose one that are not living.
Very good. So the idea of some long living thread. Okay. And this factory is going to be really a pool which keeps a list of long living threads. And we don't quite know how to create long living threads maybe, but creating long living joiner objects should not be hard. Okay, we just reuse those joiner objects later. Okay. So you use the word pool. How many of you guys have heard the term thread pool before in your life? How about, so something you learned in 410, that is the super type of pool. What kind of object is a pool that you might have seen in data structure course? Table means that you need a key access, but what's a super type of table? Stack? Well, we could do stack. So stack and table, the super type is collection. So it's some kind of collection. Okay? We could do a stack or we could do a queue. Okay? And those of you who done operating system, we could do a bounded buffer where there's only a bounded number of these. But basically a collection of some kind. Okay? And we'll go and implement it as a queue. It can implement as a stack also. Okay? So how do we get, and again, I want this to be coming out as much from you as possible because I'm going to give you the details, so it'll be boring that way. How do we get these long-lived threads around? What does that really mean to have a long-lived thread? And it means a lot of things. So what is the first thing that comes to mind? Right now, okay. Sorry? So it doesn't terminate when it finishes execution, which is kind of right and kind of contradictory, right? So Mac?
I think he means like it doesn't get garbage collected when it terminates.
It doesn't get garbage collected when it gets terminated. So we keep a reference to it, fine. But once it's terminated, how can we reuse it?
Instead of terminating when you're done evaluating an X expression, you wait for another X expression.
So we have right now a thread with a single run method, right? Or a runnable with a single run method. Somehow we need two runs, two kind of runs. One that is my current S expression to be evaluated, and one is my run known to the thread. And so we have two kinds of runs. One run is running in a loop, which is kind of what you guys are saying. And that loop loops through and executes this temporary run one by one. Okay, so there's a temporary runnable around, and the long-lived runnable around, and the long-lived runnable iterates through temporary runnables. And the long-lived runnable has assigned to it a temporary runnable. So the long-lived runnable is just this unaware of the exact computation. And the actual exact computation to be done is done by the dynamic runnable. Okay, so kind of getting it? That there are two kinds of runs to be done. One is a long-lived run that goes through a loop, and the long-lived run goes and executes the current short-term dynamic run. Okay? And after each assignment of a new dynamic run, it goes and it goes and executes that, and then waits for the next dynamic run to be assigned. Okay, so we've got waits, we've got a lot of complicated stuff going on here. Okay, but that's the basic idea. Okay, so let's see how that materializes.